All right, so in the last section, we saw Newton's first two laws of motion. And before we get to Newton's third law of motion, we're going to take a brief interlude to talk about throwing stuff, falling objects, gravity, and weight. Right? So we'll start out with section 2.3.1 of the lecture notes, talking about gravity. Right? And we've already casually tossed the idea around of falling apples and whatnot in this class, but what is gravity? Gravity is one of the fundamental forces that govern the behavior of all objects in this universe, right? And it dictates that there is an attractive force between every single pair of objects in the universe. So there is a force that is pulling me towards my laptop right now. There's a force which is pulling one star in the galaxy towards another star in the galaxy. There is a force between two people standing in the same room, a physical force, that is. So between every single pair of objects, there is a force that is trying to bring those objects together. It's stronger between objects that are more massive, and the farther away two objects are from each other, the weaker the force is. So although gravity is everywhere, it is also extraordinarily weak. It is an extremely minute force, and in our daily lives, there's basically only one object that's both close enough to us and massive enough that we directly, immediately observe the effects of a gravitational attraction. And that object is, of course, the Earth. Right? So through gravity, the Earth is exerting a downward gravitational force on every object near its surface. And we call the force with which an object is pulled in the direction of the Earth's center that object's weight. So weight is the force with which, let's say, the force with which an object is attracted towards the Earth's center. Okay, and near the surface of the Earth, what is the value of weight? Well, weight, it's a vector, just like any other force, and the direction that it points, in this case, is from wherever you are towards the Earth's center. So the weight is equal to an object's mass times this acceleration due to gravity. So here you can recognize an example of Newton's law, Newton's second law, that says that a force, the weight, is equal to a mass times an acceleration. So g, and it's often written without the vector because we know that it's always pointing down, but it is a force, and so it does have a direction associated with it. G is often called the acceleration due to gravity, but it really means due to gravity. But in this context, it's kind of specialized for when you're on planet Earth. And the value of g is approximately 9.8 meters per second squared. Right? Just like any acceleration, it has units of lengths per times squared, and in SI units, the specific value is about 9.8 meters per second squared. It's also about 32 feet per second squared, if that's easier for you to think about. So weight really refers to the force, basically, of a planetary body pulling an object close to the surface, nearer to that planetary body's center. Mass refers to this measure of inertia, right? How much an object resists changes in its velocity. And in the English language, we often toss around the ideas or the words weight and mass a little bit interchangeably, but physically they have very distinct differences. So, you can change your weight by either reducing your mass or traveling to a planet that has a weaker gravitational field, but you can only change your mass if you exercise or eat more or eat less or something like this, right? So gravity then, okay, it's a force that's omnipresent but extremely weak, and weight represents the force from, say, the Earth pulling your mass or an object's mass towards its center. Okay, so that's gravity and weight. So now we're going to talk briefly about objects in free fall. So 2.3.2, objects in free fall. Right, so weight is a measure of force, and using that force, we can easily figure out what happens to an object when it's falling. Okay? When an object is falling, And if we're neglecting the effects of air resistance, then, okay, I have some blob and it's rushing downwards due to gravity. The only force acting on this object, if we neglect air resistance, is that object's own weight, right? So using Newton's law, so we could say the weight of this vector is the object's mass times the acceleration due to gravity. Using Newton's second law, we can say, what is the acceleration of this falling object? The acceleration, well, we've said it's just given by the net force that an object experiences divided by its own mass. In this case, the only force acting on it is the object's weight, so we don't have to worry about anything else, divided by its mass. What is the weight? Well, we said up above that the weight can be written as the object's mass times the acceleration due to gravity, and then divided by the object's mass. And so now you see why this quantity g is called the acceleration due to gravity. It's because if you have an object in free fall, neglecting any other forces, g corresponds to the acceleration that that object will experience. Right? Okay, so in summary, weight, which is a force that's given by an object's mass times its acceleration due to gravity, is something we need to, really pay attention to and think about explicitly if there are multiple forces acting on an object. But if you just have an object that's in free fall and the only force acting on it is the weight, then all you need to know is this acceleration due to gravity, and that tells you what the object's acceleration is. Right? And so notice that in this expression for free fall, the mass of the object canceled out. This is one of those things that is fundamentally different between the physics that has been discovered and worked on by Galileo and Newton and researchers afterwards, and some of the historical theories, say, of Aristotle that supposed that forces and velocities were proportional to each other. Right? Here we see that accelerations and forces are proportional to each other. In this setting, objects that are the same shape but that have different weights fall at the same speed. They accelerate at the same speed, they fall at the same speed. If physics was dictated by, other laws of motion, that statement wouldn't be true, and we wouldn't necessarily expect these masses to cancel out. Okay. So that's great. That's great. So that's free fall, and free fall is a particularly simple example of motion. There's only one force acting in the problem, and you just have an object that constantly moves faster and faster due to this constant acceleration. But free fall is actually just a special case of motion of any constantly accelerating object. Constantly accelerating object. Okay. So, when an object is moving around, of course we want to know its acceleration, but we often care about the other vector physical quantities that are associated with where that object is and how it's moving. That is, we want to know an object's position and its velocity, as well as just the fact that its acceleration is given by a force divided by a mass. Right? So knowing what the position and velocity of an object are is kind of particularly simple in the case that the object has this kind of constant acceleration property. Okay. So first, let's ask ourselves, what is the velocity? What is the velocity of an object if the acceleration is constant? Well, this is actually pretty straightforward to analyze. If an object is constantly changing its velocity at the same rate per every unit time, then we can say that the final velocity of the object, v final, or equivalently the velocity of this object at some time given by t, the variable t, is just set by whatever the initial velocity of that object is, plus the acceleration multiplied by the amount of time that's elapsed. Right? And again, each of the vector quantities in this expression, each of them have a unique direction associated with them. So for instance, I can throw an object forward at some initial velocity, and its initial velocity will be moving, say horizontally forward at some speed. And then once I let go of it, gravity is the source of constant acceleration, and it's pointing down, right? So the velocity at some later time won't be horizontal, and it won't be straight down. It'll be something in between, the initial velocity and an acceleration times a time. So it might go from say, like Vf being given by some arrow in some horizontal direction to, sorry, that was meant to be V initial. to v final sometime later, being angled down somewhat. And we can figure that out by saying, suppose the acceleration is a downward vector whose magnitude is g, then we can do our trick of adding, t times this vector to our initial velocity, and then drawing, the arrow that connects, the vector quantity that connects, head to tail, the initial velocity plus acceleration times time. And this arrow here is meant to be v final. It's meant to be v final. And I see I didn't finish writing the letter t. Great. Okay. So this is an expression that tells you, again, if acceleration is constant, then you can find the velocity at time t by saying, what is my initial velocity? And then add to that quantity the amount of time that's elapsed times that constant acceleration. Fair enough. What about the position of an object that's undergoing constant acceleration? What is the position? Again, if acceleration is a constant, well, it's easy enough to figure this out because if you have a constant acceleration, you have an object's velocity that's kind of very smoothly, uniformly changing over the course of time, right? And so you can say the average velocity over the entire time that you care about, v average, is just going to be given by half of the initial velocity plus whatever the velocity at the end is, vi plus vf. Okay, and we have an expression up here for what the final velocity is in the case of constant acceleration. So we can substitute that in. I have 1/2 times the initial velocity plus acceleration times time, which if you like, you can rewrite as the initial velocity plus 1/2 times the acceleration times time. Okay. Given that this is the average velocity you experience, you can immediately use this to figure out what your position is. So your final position, let's use x for position and call it x final. Well, that's just given by your initial position plus t times the average velocity that you experience, right? And so if you substitute in what we've figured out for the average velocity, you realize that this is just the initial position plus your initial velocity times time plus 1/2 times your constant acceleration times 2 powers of the time, 1/2 at squared. Right? Fantastic. Okay. So this is a general set of vector equations that tell you if you have constant acceleration, regardless of what the source of that constant acceleration is, if you have constant acceleration, your velocity at any time is given by your initial velocity plus acceleration times time. You can figure out your average velocity over the course of whatever amount of time you care about. And then you can figure out your final position by asking where did you start, and then, what is time times the average velocity with which you moved over the time you care about. And you can expand that out to x initial plus time times v initial plus 1/2 acceleration times time squared. Okay. So let's do a quick demonstration, I suppose, of what it looks like when you throw things. Throwing stuff. And so again, let's pull up a little illustration that I already put together. Very good. Okay, great. So what are we showing here? We've got you at time 0, and maybe you're not entirely happy with the way this lecture is going, and so you take a tomato out of your pocket and you throw it at me at time equals 0, right? So the idea here would be, you at time equals 0 impart a lot of force and then let go. So initially, you have some velocity that I've drawn with this blue arrow here. So this is v initial, right? And the position here is, this is x initial. Okay. One of the nice things about writing down these vector equations is that the different components of these vectors kind of don't communicate with each other. And what do I mean by that? In this case, I'm drawing things so that, velocity has a component that's kind of horizontally and vertically, in the x and y directions, if you like. And once this tomato leaves your hand, the only force acting is the force due to gravity, right? And it's a constant acceleration that points down. It's a weight, right? It's a constant, the force here, the weight, is a constant force. The acceleration doesn't depend on the weight of the tomato, so you just have an acceleration g pointing straight down. The fact that it's pointing straight down means it doesn't influence the horizontal component of velocity whatsoever, right? So in this expression, in this throwing a tomato example, I have x initial, it's just wherever it is. V initial is some vector that's kind of, let's say at a 45-degree angle, right? You're throwing it at some speed with both a horizontal and a vertical component. And you can break those components down into the kind of component in the x direction, which maybe I'll call Vx, and the component in the y direction, which maybe I'll call Vy. And in this expression, acceleration is something that only has a component in the y direction. It points in the negative y direction, right? And so what that means is that over the course of this entire trajectory, because there's no force pointing in the x direction, there's no acceleration in the x direction, and so the velocity in the x direction stays completely the same. So for every second that elapses, the total horizontal distance traveled by this tomato is exactly the same. And the extent to which it isn't in this illustration is just a fact of me making the illustration poorly, but it's pretty close, right? So, it's nice. In these kind of vector representations, these equations look sometimes complicated, but they let you completely separate out directions that don't talk to each other. So in this case, the velocity in the x direction is completely independent of any acceleration. And so if all I care about is, if all I care about is, say, the x component of the position at time t, so let me write that as, I have my vector x of t, which I'll write as some x component and some y component. The x component is going to be just whatever the x component of x initial was, plus whatever this component of velocity in the x direction is times time. In the x direction, there's no acceleration, and so you don't have to worry about this piece. In the y direction, it's the only place in this example where the constant acceleration comes in, and you can see that in this picture, the y component starts out at some value, acceleration is pointing down, force is pointing down due to gravity, and so at 1 second, the y component is a little bit less. At 2 seconds, it's completely gone to 0, and then it starts moving downwards, right? So at time 3 seconds, the velocity in the y direction is negative, whatever the value it was at 1 second over here, in this example where the total trajectory is 4 seconds and it hits the peak at 2 seconds, that is. And at 4 seconds, you find that it's going down exactly as fast as it was going up at the very beginning of this trajectory. That's kind of an artifact of choosing a perfectly symmetric trajectory, but the principle is the same. This idea that you can separate out horizontal and vertical components when a force or an acceleration is only present in one of those two directions.